Today's video is going to be a continuation from the previous video where I outlined the overview of a project that I'm trying to create. Basically, it's going to be a capacitor leakage tester with a lot of features, hopefully. In the first video, I outlined the basic idea, the principles that I'm going for in the leakage tester, and I go through the design of the first stage of that device, which is a capacitor discharger. If you haven't watched that video, I recommend that you watch that one before watching this one. In this video, I'm going to attempt to design and build an auto-ranging analog meter using this guy here. And the basic idea is to have this auto-ranging in 4 different ranges. At this point, those 4 ranges I anticipate being 100 microamps, 1 milliamp, 10 milliamps and 100 milliamps. But as I haven't actually designed the meter yet or even really thought about the concept, that may well change. So if you want to see an auto-ranging analog current meter, this is the video for you. Let's go. So the first question to be answered is, how do you go about changing the range of an analog meter such as this one, which has got a range of 100 microamps? How do I go about increasing the range of this meter? Well, that's actually not that difficult to achieve, and it's something that's been done for many years. Obviously, historically, these were really the only type of current meters that you could get before the advent of digital electronics. So many years ago, what you would have to do is to put what's called a shunt across the meter. Now basically all that is a resistor. So in this case we would just simply add a resistor across the back of the meter, and if we calculate that resistor correctly, then we can calibrate the range in factors of whatever we want. So I'm going to go to a pen and a piece of paper and going to try and explain how that works. Before I do that, the first fundamental thing that I need to know to be able to do the calculations is what voltage this meter requires across it to measure full scale or close to full scale. So I'm going to do that first, and then we can go to the paper and I'll show you how to calculate the resistances or the resistors that we need. So to do this, I'm just going to use quite a simple gadget here. I've got a constant current and constant voltage source here. I'm literally just going to connect that across the meter. Let's turn that on, put this so guys so you can see it. I'll turn that down to minimum. So this isn't entirely accurate, especially down when we're talking, very little output. This is a 0 to 22 milliamps, and in the microamp range it's not overly accurate, but it's good enough because all I want to do is to measure the voltage across the meter at full scale or thereabouts. So let's get the fluke out. So I've got this set to DC millivolts, so I'm just going to crank this up till we get to somewhere near full scale. That's a little bit over, we'll go a little bit under to start with. So measure the voltage across there now. So that's about 260 millivolts. So we'll use that as our reference. Doesn't have to be entirely accurate because, as you'll see later, we can actually and we will need to put some potentiometers on this so we can actually calibrate the ranges a little. So 460 millivolts is good enough for now. So I'm going to try and explain this as simply as I possibly can. So if we take our ammeter here and we've got the terminals. So this is 100 microamps, and at 100 microamps we have 0.46 volts, and that's across the meter. Now if we want to, say, increase the scale of this to, let's take for example, we'll go up one range, so we'll say we now want to make this a 1 milliamp. Okay, what we basically have to do is we have to put a resistor across the meter in here, and then some of the current will go through the ammeter as we want, and the remaining current will come down, go through the resistor and bypass the meter. So we need to calculate the value of this resistor. So if we imagine in this scenario that we want we still want 100 microamps to actually flow through the meter, because that is the range of the meter. Okay, so that means that actually through the resistor we want 0.9 milliamps to pass through the resistor in this scenario. So therefore the value of the resistor will be 0.46, because that's the voltage that we actually need for full scale deflection, and then we will divide that by 9 milliamps, sorry, 0.9 milliamps, and that will equal, let's just go to the calculator. Okay, that comes to 511 ohms. So the actual, obviously the values for that are 0.46 divided by 0.0009. Now all we have to, so in that scenario, if I now put a 500 ohm resistor across that ammeter, then it will change the scale of the ammeter to a 1 milliamp scale, and in that scenario 100 microamps will still be passing through the meter, and 0.9 milliamps is at full scale deflection. 0.9 milliamps will be passing through the resistor, and that will give us a range of 0 to 1 milliamp. Now we can repeat that process for the next ranges, so we can say we can repeat the process for a 10 milliamp range and a 100 milliamp range. So, and we do exactly the same scenario. So we need 0.46 volts because that's full scale deflection, and then we divide that, and then we assume in this scenario that in the 10 milliamp range we will have 9.9 milliamps passing through the resistor. So we divide that by 0.0099, and that will give us the next one. And then the same token for 100 microamps, 0.46 volts divided by, and then again in that scenario we'll have 99.9 milliamps passing through the resistor, so we would divide that by 0.099. Okay, so I'm just going to do the math on those, and I shall be back in a moment. Okay, so these are the figures that I've come up with. So obviously for 100 microamp range we don't want any shunt across it at all, that's just going to read 100 microamps. Then for 1 milliamp range we need a 511 ohm resistor. For a 10 milliamp range we need a 46 ohm resistor, and for 100 milliamps we need a 4.6 ohm resistor. And in order to make these adjustable, we can actually put a potentiometer across the resistor. So the figures that I've come up with would look like something like if we have a 560 ohm resistor with a 10k potentiometer, and then we'll have a 56 ohm resistor with a 1k, and then we would have a 5.1 ohm resistor with a 100 ohm potentiometer. And then if we do the calculations on those, so it's basically just we'll just do the two resistors in parallel, which will give us the lowest reading, and then obviously we can go lower than that. So a 560 ohm with a 10k across it, let's just go to the calculator, comes out as around 530 ohms, which is the max, and then that will obviously we can go down from there. The 56 ohm with a 1k across it will come out as about 53 ohms. Obviously we can go down from there, and then the 5.1 with 100 ohms across it comes out as about that comes out as about 4.8 ohms, and then obviously we can go down from that point. So we can see that to enable calibration and adjustment of these values are my nominal values, and with if I take, for example, these values, then I can go from 530 ohms down, which puts 511 in range. With the 56 ohm with a 1k across it, I can start at 53 ohms and come down, that's in range. And then with the 5.1 ohm with 100 ohms across it, that puts the maximum at 4.8 coming down, which then again is in range. So again, these values may not be set in stone. These are all calculated values based on this meter here, but we'll see how that goes. But yeah, that should be quite close, hopefully. So to go to the next step, if I draw the ammeter here, okay, and then I'm just going to call the resistance ranges R1, R2 and R3 for the different ranges. So R1 would be the 1 milliamp, R2 10 milliamps, and R3 would be 100 milliamps. So to actually get this to work, so effectively all we need to do is to put a switching element in here with R1, switching element here, R2, and a switching element in here, R3. Okay, and our current would then come in here. Okay, so that way with all three switches open, we'll be reading the 100 microamp range, and then with this switch closed will read the 1 milliamp hour range, this switch closed will be the 10 milliamp range, and this switch closed will be the 100 milliamp range. Okay, and it's as simple as that. Now the switching elements we need to discuss a bit further. So if I wanted this to be a manually operated switch, I could literally have a 4-position switch and switch in each resistance into each range and do that manually. But that's not the idea here. We want to make this automatic. So how do we go about making this automatic? Well, I've had a bit of a think about it and I've come up with a couple of ideas, and I think the most promising one is the one I'm going to try first, and hopefully that will actually work. So what I intend to do is I'm going to have, obviously I need to measure across the actual ammeter itself, and I'm going to have a couple of measurement points. So I'm going to call this M1 and M2. Now obviously we know that for full scale deflection of this meter we have 0.46 volts or thereabouts. So if we know that, so if we can actually read the voltage across the meter itself, we can say that if it goes up to 0.46 on any given range, then it's at the maximum range. And to the same token, if it goes down to, let's say, 0 or just over 0, we know it's at the bottom end of the range, and therefore we should be able to go up a range. So with that in mind, what I intend to do is actually monitor the voltage across the ammeter, and probably at this point I'm going to say I'm going to have 2 comparators. Okay, so if we say that we'll have 2 comparators, and there'll be a reference voltage that will be adjustable, and then the other side will actually be the input from the meter. So that's your first comparator, and then the second comparator will be this, actually probably be the opposite way around, but we'll worry about that in a moment. So your second comparator again will have a reference, which will be adjustable. Then the output of those comparators will then, we can say, so if we set our reference here to, for example, 0.1 volts. Okay, so if we have, for example, if we have the reference voltage on this one going into pin 2, and which is, for example, if this was, let's take a common comparator, and LM393, and then we had the input going into pin 3, and on this one, if we reverse that, so we have the signal input going to pin 2 and the reference going into pin 3, what will happen is that if we go to this one, what will happen is when the reference, when the input gets above the reference, then the output will go high, and then this one, when the output will only go high when the input is below the reference. Okay, and in that way we can actually say below, above. Okay, so there we have 2 positive going pulses, but critically one is when the input is below the threshold and one is when it's above. So in that way we always know if the meter is at our threshold or below, or at our threshold and above, and that is quite critical in my thinking, that we need to be able to know that to make this a successful auto switching ammeter. So then the basic idea then will be just to probably, and again, this is in a very simple format. We've got other things that we need to consider with this as far as our capacitor leakage tester is concerned. But fundamentally we can just say, okay, well, I can feed this into a controller, okay, and the controller will say, okay, I've now got 3 outputs for my ranges, 1 milliamp, 10 milliamps and 100 milliamps. Okay, and the controller will know if it's below or above range. Okay, then for example, it will know what the current range is. If it's below range, then it will need to go up a range, and it's above the range, it will need to go down a range. Now obviously there are limitations on that because we're only talking about a specific circumstance here, so we know we've got to make some assumptions as far as the actual current that we're going to be seeing. So for safety reasons, we can just put a diode. We can just put a diode across this meter. We know that this needs 0.46 volts for full scale deflection. If we just put a diode across the meter, we can actually protect it because it will clamp the maximum voltage to about 0.6 of a volt. So even if we get this system totally wrong and we try to put 100 milliamps through a 10 microamp meter, which would normally probably blow the meter up, burn the coil out inside the meter, we can actually put a clamping voltage of 0.6 of a volt on that, so it will not do that. So I will do that on the final version, or even the test version, to try and protect the meter a little bit, because I'm sure during the construction and testing of this device, I'm going to get this wrong quite a few times in the sequencing, the programming, the positive going pulses, and etc. There's quite a lot to deal with. So fundamentally, what we can do is we can have a system like this with 2 comparators. So fundamentally, that is the basic concept. But there is one more thing that we need to consider, and I will talk about that in just a moment. Okay, so the biggest downside to this particular system is that we're currently relying on things like comparators, and microcontrollers, okay, which all have quite a limited supply voltage. You know, somewhere a microcontroller is probably going to be like 5 volts maximum. Comparator maybe up to 30 volts, something like that. Okay, now in this system that we're trying to develop, we can actually, we're going to be designing, obviously across the meter is only ever going to be, 0.6 of a volt if we put a clamping diode on there. But the actual device under test is going to have a potential here of, let's say 800 volts. Okay, now although we're not actually going to have 800 volts across the meter, we are going to have an 800 volt potential, which we're going to need to measure, and we're going to be measuring at that potential. Unfortunately, we're going to need to isolate all of these electronic components from the 800 volts. And what that means basically is that any supply voltages to the comparators and the microcontrollers potentially are going to need to come from an isolated supply. which will not is then not referenced to the ground potential of the 800 volts. So I've got to have a little bit of a think about how I'm actually going to achieve that. The first thing that springs to mind is that I literally will have a transformer here with supplying the so it'll be a separate winding or a separate transformer supplying any power to the devices here. We'll probably need to use some opto-isolators to separate these signals from the inputs to the microcontroller. So if we'd imagine that they may well be like an opto-isolator type deal in here, something like that, supplying the signal to that, and then I could have the actual supply for this isolated, and that way we can literally measure across the ammeter into the comparators, which will have an isolated supply, so they'll literally be measuring across the voltage across the comparator rather than with reference to the ground potential, and then opto-isolate the inputs to that. So that's kind of what I'm thinking. But at this point I really don't know how I'm going to achieve that exactly, so that is the next stage for me. So in the next section of the video I've hopefully have worked that out and have something else to show you. Okay, some time has passed and I have found something that looks to be very interesting to me on this particular project. And this is an isolated DC to DC converter. Now this particular one is a 1 watt one, but they do these in higher wattages. Haven't calculated how many watts I need yet, but I just thought I'd get one of these guys and test it, because the crucial part here, as we can see from the data sheet, that they actually have an input output isolation of at least, or tested to 1.5 k volts DC, which is brilliant for what we want. So I intend to I've got one of these guys on my desk here. Hang on for a moment. Here it is. I won't bother zooming in, you don't need to see it, but what I am going to do is I'm going to actually test the isolation voltage of this. So I have one of these, in fact I've got several of these testers here. Now the pin out on this guy I think is pin 1 is ground, pin 2 is 12 volts, and then on the input, and then pin 3 is ground and pin 4 is the output voltage. So we'll start by, so I've got the meter, I've got the tester here set for just over 1000 volts, which is more than enough for me. So I'm just going to test this. I'm going to go between pin 1, if I can, try and not blow the thing up. Okay, so I'm on pin 1 and pin 3, which should be the two grounds, and yeah, that's successfully passing the test because it's going up to the test voltage. It's not shorting it out. That's good. And then we'll do the same on pins 2 and 4. Okay, test again. Yep, again, so that's good up to over 1000 volts, which is more than I need, and the data sheet says 1500. So that is step 1 of my problem solved. I can now use one of these to create an isolated supply for my project. Okay, a little bit of time has passed again, and I've been looking through AliExpress what they have available, and I've actually found this on AliExpress. So this is actually a 5 volt in, 5 volt out, 3 watt device, similar specification to the one I've just been in the video. I have tested this, and again this is good to over 1000 volts, so this is very good, a very good item for what I need. And while I was looking through some stuff on AliExpress, I also found this. This is a very nice little LM393 comparator module, and it's actually very good. It has a built-in reference, adjustable reference, and it's got various outputs. I think it's got a I don't know, actually I'm not sure at the moment because I haven't opened it, but it's got a couple of different outputs which I'm sure I can use to interface to an opto-isolator, and it's got the input voltage and the sense voltage on this side. So again, this is almost ideal for what I want, ideal for half of what I want, but again I should be able to modify this quite simply to give me the other half of what I need for the overall design. So again, this is very encouraging. I've purchased 4 of these, and I will be investigating the operation of these quite shortly. The other thing I've found, this is one example of a pre-built opto-isolation board available on AliExpress. Again, I've got a couple of different variations of these, which I'm going to use to experiment with. But again, it's a nice little module which will make my life a lot easier. And I've also got one of these, a 4-channel opto-isolated relay module designed to be interfaced to microcontrollers, etc. Again, this will be quite ideal for what I need for switching of my resistances in and out for the current meter. So I think I've found a lot of the items that I actually need to be able to build something. So I'm going to go away now with some of these items and see what I can come up with. Okay, some more time has passed. I have been a little bit busy these last few days working on this. So this is the first part of the module that I've come up with. So this consists of 2 of those LM393 comparator modules that I was discussing earlier, which were purchased from AliExpress. I have modified one of these. Let me just zoom in on that. I've literally just swapped the wires on pins 2 and 3 over to have the effect that I need for this module. So this top module is for the maximum range, if you like, and which will give an output if it's above the set point, which is set from this potentiometer, and this one will give an output if it's below the set point set on this potentiometer. I have incorporated the isolation DC to DC converter, which is this guy here, as I showed you earlier. It's a 5 volt in, 5 volt out, 3 watt device. I've got a few extra bits and pieces on here just for testing purposes, a couple of LEDs, etc. I'm not sure if I'm going to use those at the moment because all this stuff has got built-in LEDs. So I have got, at the moment, I've got a double opto-isolation module here going on. So as you see, I have actually modified these boards a little bit. I've changed the plugs on them to more suitable plugs for what I want. So I've literally got coming in, so this is the voltage in, and the ground, which is coming from the isolated the DC to DC converter, and then the actual measurement voltage is on the yellow wire, which is coming basically from this yellow wire here. Let's just zoom back out again. It's coming from this yellow wire here, which will be the sense wire to the actual meter itself. And then so I've got the 2 opto-isolated modules here, and then the 2 outputs here. So this is supplied from 5 volts, and it can be any 5 volts because it's going into this DC to DC converter. So the power from this module is all supplied from this converter here. So this is actually totally electrically isolated. The only thing that's actually referenced to the common ground reference will be the outputs of the opto-isolators. So then in addition to that, I have here, so this is all connected together at the moment. So I have here, and this is pretty much for testing purposes, but I have the 3 resistors as specified. I've then got that going into the relay module that I showed you earlier. So again, each one of those relays literally switches one of those resistances in, and then the output is on this wire. That is in turn now connected to, I've got an Arduino Nano here, and I have attached a small OLED screen onto it, which does have some buttons. I haven't done anything with the buttons yet, and so far that's it. I have already started to do some programming on this, and in fact I do believe that I have a kind of working system going on. So I'm going to go ahead and connect all of this stuff up, then try and demonstrate the operation of it to you guys, which may or may work out well or not, I don't know. Let's try. So give me a moment, please. Okay, so this is the setup that I've got so far. Now it's going to be a bit awkward, so I've got a lot to get into shot, but I'm going to do my best to try and get it all in. So the first thing I need to do is to try and angle that guy up so you can see that a bit better. What have I got to put under there? Okay. Right, so that's the the microamp meter. This is the display, the screen that I've added. So hopefully you can read that. So at the moment it says meter range is on 100 microamps. I've got my current source here actually set to 0, but I just want to demonstrate that this isn't entirely accurate, this guy. Because we can see that I've actually got 11 microamps actually going into the meter, and we can see that on the scale there it's saying 10. So you know, this thing is actually pretty accurate, and the display on this isn't overly accurate. Anyway, that's neither here nor there. We can do all the calibration later. I've got my calibration pots here again. I haven't really, oh, you can't actually see those. Let's try and get those in the shot. Yep, so I've got my calibration potentiometers here. This is just a test setup. I will be using some closer tolerance resistors, etc. in the final version, but this is just for testing. It's working okay. So I'm just going to move that back out of shot because there's so much to get in. Okay, so hopefully you can see the LEDs that will be on the opto-isolators here. So the one on the bottom here is for the under range, and the one on the top is over range. So the only way I can get the under range to go on is actually to switch this meter off. Okay, now we can see that the meter's gone pretty much to 0, and you can see that on the display here, it actually, hopefully you can read that, it says under. Okay, so I actually have the under and over inputs being displayed on the meter, so we know whether it's getting the signal, and we can see that the LED, hopefully you can see that LED is on. Probably not. Let's just put the colour over it there. So the LED there is on for the under range, and that's being displayed on the screen. And when it goes over range, this will change to over, and the other LED on the other opto isolator will come on. So let's just make a bit more room. I'm actually going to, what I'm going to do, I'm going to take that out of circuit. Now I've demonstrated the fact that this meter on here isn't accurate, I can take the digital meter out of circuit. Okay. So now we can crank up. Okay, so let's just do that again. So I'm going down range. Okay, so we've gone down below the 1 milliamp range. We're now onto the 100 microamp range. We've got saying about 0.2 thereabouts. Okay, so we go up to the 1 milliamp range, and we'll continue to go all the way through the range until it trips onto the next one. Okay, so now we're on the 10 milliamp range on the meter. we've got about 1 milliamp coming out here, just over 1 milliamp, just over 1 milliamp on the meter, and then we'll go up here, so we need to go past 10 milliamps now for this to go over range again, which is a lot of knob presses. I have got this configured to go up quite slowly because I needed it to go in smaller steps at the bottom end, and it's a bit of a pain to reconfigure every time, so I just prefer just to keep turning. So we're approaching 8, 9, okay, so again we've gone over range, so we're back into, so we're in the 100 milliamp range now, so I've got about 11 milliamps going in. You can see we've got about 11 milliamps on the meter there. Now this current, this constant current supply will only actually go up to 20 milliamps in the current setting, so all we can do is go up to 20 milliamps. But you can see it's slowly creeping up as we approach the 20. So that's down about 20 again. So I mean, I do need to calibrate all of this, but this is just for an idea. So I've got my potential just as an adjustment, so I can just increase that up to 20. There is a bit of parallax on the camera, so it is actually on 20 if I just move the angle a little bit. So there, so, and then I can just quickly demonstrate going down. So again, there's a lot of rotation here. So we can see the meter range is on number 4, which is 100 microamps. And go down, 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 down. I'll do this bit and fast forward, I think. Okay, so we've changed. So we've just changed range. It's now on the 10 milliamp range. We've got about 6 milliamps, on there, and we'll keep coming down. Okay, changed again at 0.6. So we're now on the 1 milliamp range on the meter. We've got about 0.6 milliamps and about 0.6 milliamps on the analog meter there. And then we'll come down again. It's a lot quicker now, thank God. And we'll go range down again. Okay, we're now in the 100 microamp range. So this is just the meter itself. So all of my relays are switched out now. It's literally just the wiring, which obviously it's a bit of a mess at the moment, and that's affecting the accuracy as well. When it's all set up properly with decent cabling, then that's going to be the most accurate. But anyway, we can see that this is saying about, I don't know, 500, about 50 microamps. The meter's saying more like 35, but there you go. So the basic concept is all there, and it just needs a bit of refinement and some tidying up. I will be releasing the circuit diagrams and the code for all this stuff when the whole module is complete. If I manage to complete the module, that is. If I don't manage to complete the module, I will release the schematic diagrams and programs to the points that you can see in the videos. So if I don't manage to go any further with this project, which I think I will, but if I don't, then I will release the schematics and the programming for the automatic analog current meter. So I hope you enjoyed that. I hope that's I've enjoyed it. It has been a little bit of a challenge with the getting the programming right and all that kind of stuff. It has been made a lot easier. The fact that I haven't had to make my own PCBs for the optocouplers and for the comparators, all that has been made a lot easier by using the modules from AliExpress, and I'm really happy that I found those. Obviously I did have to modify one of those a little bit, but other than that, this is all using standard stuff from AliExpress, which is actually really good. So I hope you enjoyed that, and please leave a comment in the comment section if you've got any questions related to this. And I can now proceed with the third part of the video, which will be the power supply section. So thanks for watching, and I shall see you next time.